Welcome everybody, good afternoon. Welcome back to this online learning weeks. Today we have a very special surprise in store for you, coming live from inside the Arctic Circle. It's our friend Dr. Cordian Riener. He's going to speak to us about symmetries in semi-definite programming today. And in the next 2 weeks, he will speak more about symmetries also in real algebraic geometry, polynomial optimization, and so forth. So just before I give the word to Cordian, I just want to remind you how this works in case you are new. Please just keep your microphone and your video off. There will be opportunity to ask questions through the chat box. So Cordian will give us opportunity to ask questions, and then we can just type those in the chat box and he will answer us. We will have plenty of time for questions because it does not get dark where Cordian is at this time of the year. So without further ado, I give the word to you.
Thank you, Etienne. Thank you, everybody, for actually joining. It's absolutely right what Etienne said. It doesn't get dark at the moment. And although I'm over the polar circle and it's hard to see, I'm actually also wearing a t-shirt today. Although maybe, I mean, the temperature is maybe not really appropriate for that. But anyways, so I'm very happy that so many people are here. And I want to tell you a little bit more about something that is integrated in lots of my works, namely symmetries in algorithmic questions in real algebraic geometry. So the whole talk is supposed to be rather basic and just an introduction, and it's aimed towards the ERS of our POEMA network. And I hope that you all get something out of this for your PhD thesis projects. And because Etienne wanted me to start slowly, let me start slowly with something that is rather uncommon in mathematical talks, namely a picture. So before I go into details, and the details might be messy, I want to start this talk with a picture that I like very much. So, okay, now there was just a helicopter. There's a helicopter landing. I'm not sure if you can hear this, but I try not to get distracted. So have a look at this picture. Suppose you are at the museum and you look at this picture. And later on, you come home and somebody wants you to describe this picture. So, I mean, if you just gaze at this picture, it looks awfully complicated with a lot of things popping up, different colors, different shapes. However, because you're a mathematician, you have paid close attention of a very fundamental structural property that this picture has. Namely, you see here, this picture is made up by certain reflections on mirrors. It's basically a kaleidoscope picture. And because you realize this while you were in the museum, you realize that you actually only need to remember this small part of the picture, and you need to only analyze this small part of the picture. But however, when you come back home and you want to explain to your partner, to your parents, whoever, what the whole picture looks like, I mean, it's not enough to only have this information. You also need to contain the information that is given by the group structure, by these walls here, in order to unfold the picture again to everybody. So I'm not sure if this picture makes a lot of sense at the moment to you all, but I hope you can keep this a little bit in mind as a sort of meta-guiding principle throughout this talks and the next talks. So what will be this talks and the next talks? So as Etienne already mentioned, today I will mainly focus on symmetries in semi-definite programs, and for that mainly I will focus on so-called linear representation theory. So in fact, I want to give you first a glaze, an introduction, an invitation to representation theory, which is a beautiful part of algebra. And of course, I cannot get into all the depths of it, but I hope that afterwards you will be able to get some insights, gain some insights, and take this further on your own if you want to. And then I want to show you how this can be actually used to simplify semi-definite programs. And in the next week, I want to build on that and then start to go towards polynomial optimizations with symmetries. And then we will meet another important player from algebra, namely invariant theory, which is also a very classical topic. And also, again, then I will not be able to basically cover the whole topic, but I will hopefully be able to prepare you to understand where it's necessary in polynomial optimization. And for the last week, which is still a little bit vague in the title, is I want to give you some concrete applications, how these techniques actually were used, are used in concrete cool applications. Okay, so far I see there's no questions, so let's move on. And let's really dive into it very quickly. And whenever it's too quick, or whenever you feel I should explain something in more detail, please feel free to put into the chat box. So the main definition that we need to understand representation theory is the definition of a representation. So we will start throughout this talk. G will always denote a group that I will assume to be finite, and G will be a field, and I will assume that this field is actually of characteristic 0 and algebraically closed. Let me also point out that this is some sort of a restriction, but most people in our field are exactly familiar with that. So we actually only work in characteristic 0. However, if you're from the algebraic side, working in positive characteristic might spice up the situation a little bit more, and it will create some further problems, but we shouldn't worry too much about those here. So the fundamental notion is the one of a representation. So a representation of a group G is nothing more than a finite dimensional, in our setup, finite dimensional vector space V defined over K together, and that's important, it's not only the vector space, together with the group homomorphism that takes the group G into the general linear group of our vector space, so into the linear invertible transformations of V. Okay? So in some sense, we start with a group that is somehow abstractly defined, and we make this group concrete by having it act on a vector space. The dimension of the vector space is in this context then also referred to as the degree of the representation. And so normally whenever you have two vector spaces, when they are of the same dimension, they are isomorphic. However, here in the setup of representations, it's a little bit more tricky. So we have two vector spaces, V and V prime, and together with a group homomorphism of the group G into the general linear group. And those two vector spaces are isomorphic as representations if we can find an isomorphism between the vector spaces that additionally satisfies that it's compatible with the group action. So that I can actually independently apply G on the left or on the right side here. Okay? And another important thing that we should remember, up till now we haven't selected any basis. However, we all know that vector spaces have bases, so whenever you choose a basis for the vector space, then you actually make the general linear group concrete as a matrix group, and then all we are saying is that we take our group and we identify our group with a subgroup that I will always refer to as MG of invertible matrices. Okay? So that's a lot to digest. So let's just have some easy examples. So one of the easiest example of a representation is when I take a one-dimensional vector space and I take a very, very easy homomorphism, namely I map every element of my group to the one element. So, to the one matrix, if I wanted to look at 1 times 1 matrices. Okay? And this is then called, because it's rather trivial action of the group is not doing anything on my one-dimensional space, this is called the trivial representation of a group. Okay? However, as I just mentioned, vector spaces of the same dimension normally are considered to be isomorphic. However, let's see an example that I can also take a one-dimensional vector space and I take the two-element group with the two elements E and E inverse, and I define the representation in the way that I send the identity element to 1 and its inverse to its inverse to -1. And then this also defines a representation of degree 1, which is not the same representation as above. So for the 2-element group, we already have seen 2 distinct representations. So more general, I can look at the following setup. I can take a finite set S and have an action of G on the set S, and then look at a very simple vector space. Namely, I look at the vector space that I get by looking at the direct sum of copies of K with basis elements that are indexed by my set, by the elements of my set. So, and then I can naturally define a representation of my group on this vector space just by defining it like this, so that I say, well, the group acts on the vector space via its action on the basis, and the action on the basis is just according to the action of my group on the finite set S that I started with. Okay, so when I do this, what do we get? We get a representation. Its degree, its dimension is exactly the cardinality of the set S, and the matrices that I get when I look at the matrices with respect relative to the basis of these ESs, they are exactly permutation matrices. Yeah, they contain only zeros and ones. And such a representation then naturally is called a permutation representation of a group G. And a very special but important case of such a permutation representation occurs when I take my set S to be my group that I started with, and I let act G on itself by left multiplication. And then what I get is called, is a representation of degree exactly the cardinality of G, right? Because that's the way we define this permutation representations. And this is then called, it's a special permutation representation, this is called the regular representation of G. So you have seen 4 different examples of a representation, and I hope the basic concept, which is rather easy, is understood now. I'll move on. So there's another notion that is sometimes also used and is much more convenient to work with, and that's the notion of a G module. So whenever I start, again, with a finite group, and I take a finite dimensional vector space, and then I can say that this vector space V has the structure of a G module if I have an action of my group G on V, a multiplication that I define, just I take for every element G in G and V in V, I define this left multiplication just in the natural way, and I want to make sure that it satisfies these properties so that it's compatible with the group, so that the identity doesn't do anything, and that I can distribute the multiplication, and it should be also compatible with the linear structure of my vector space. So this seems like a completely different notion. However, these 2 notions are in fact equivalent, and you can think about why they are in fact equivalent at home during the exercises. But essentially, it's just translating from one of the notations to the other notation. The big advantage of this G module is just that when we go back, maybe let me say this, when we go back to the representation, we always have to carry around the vector space and the explicit homomorphism. But when I just talk about the G module, I don't need always to refer to this homomorphism. So it's kind of an easier way to talk. Okay, and let me also come with another definition. So, whenever we have vector spaces, we can look at the homomorphisms between vector spaces. Now I want to look at the G homomorphisms. So I have 2 G modules, V and W, and then I want to look at all the linear maps between the vector spaces that are always also commutable with the group action. And this is called, respect not only the linear structure of the vector spaces, but also the structure as a group module. So this will be denoted as hom G, V, and W. And in the particular case, when we look at endomorphisms, I will look at the G invariant endomorphisms of a G module. Okay, so far no question. It's a little bit odd, I have to say, when you talk to your screen, nobody is there and it's completely quiet, but I hope you're still all there. This is very new for me in that sense that I've never experienced a lecture like this, actually talking to myself. But let's go on a little bit. So there's another important notion that you might come across, and that's the notion of a character. So what's a character? Again, we have a group. To that group, we associate a G module, V, and I take any basis of my module V, and I look at the corresponding matrix group that I get. So in some sense, I associate to every element G a matrix M of G. And then the character should be a group, should be a function that takes a group element and maps it to my field K. And it's defined in a very natural way. So I take the trace, the character evaluated at an element G should be the trace of a matrix corresponding to a basis, so that corresponds to G. So the trace of M of G for all G. Okay, so this would be now the ideal moment to ask in the audience if this is actually well defined, because somehow on the way we used matrices and we used bases. But since it's really hard to see if you want to answer anything via the chat, let me just give you the answer. Well, this is kind of, it looks arbitrary because we have this choice of a basis to get the matrix representation. However, as you all, okay, yeah, very good, very good. I just got a private message, but I will answer that later. So, sorry. The trace does not depend on this choice because we, as you all remember from linear algebra, the trace of two matrices, of three matrices, when I do a base change, actually I can interchange cyclically. So essentially the trace does not depend on the basis that we've chosen. So the character actually only depends on the representation itself. And given two characters, Xi1 and Xi2, we can also define an inner product on the space of all characters, which is just, I mean, I take the products over the individual character evaluations, and I divide this by the cardinality of the group. So it's an easy exercise to show again that this is an inner product. Shouldn't take too much into that. So why are characters actually interesting? So characters have the advantage, as I just pointed out to you, that they only depend on the representation and they don't really care too much about how the representation is defined, what vector space we're actually living on. So, so this makes them a very nice tool in the sense that this defines a function from the group to my base field K. And in particular, those functions have the property that the functions are constant on conjugate classes of my group G. So whenever two elements are conjugate, again, I can get the one from the other by conjugate, then the trace is the same. It's an easy exercise for you to do in the exercises to see that, but it's essentially the same argument. It's cyclically shifting around the matrices that correspond to that. And the interesting thing is that if I have a representation that is defined by a direct sum of two representations, then obviously the two characters are additive. And if I multiply, then they are multiplicative with a tensor product. That's just because we all know that the trace of a matrix is only the sum of its eigenvalues. And if you do a direct sum of vector spaces, well, you get, for the matrices, you get the sum of the individual traces. And the same for the eigenvalues in the tensor product. We know that the eigenvalues are the products of the eigenvalues of my original matrices. Okay. So now we are coming a little bit to the interesting definitions. So now, up to now, this was all very basic, just introductory definitions. And now let's go a little bit to interesting representations. So again, I start with a finite group, G, and group module V. And then I say that a subspace W is G-stable or a G-submodule, well, one, when it is closed under the action of G. So whenever I take an element out of V and an element of the group G, and I let the element act on W, I will stay in W. So whenever I find a subspace that has this property, this means that the subspace is a G-module of its own right, and or is G-stable or a G-submodule in that sense. And if we don't find a non-trivial, that means a subspace that is stable, so a subspace that is neither the zero subspace nor V itself, then we will say that this G-module is irreducible. Okay? Why irreducible? Because I cannot reduce it, otherwise I will call it reducible. Okay, that's very easy definition, but let's look again at examples. So I claim that every one-dimensional representation of a group G, or every one-dimensional G module, is in fact irreducible. Why? Well, I mean, it's a vector space of dimension 1, and I mean, it cannot contain another vector space of positive dimension. Okay, so particular is irreducible. Now let's look at something that is reducible. Let's take the group, again, the permutation of two elements, and let's have it act on the two-dimensional vector space V that are indexed with the elements with the basis E1, E2, and I want the group just to permute E1 and E2. Now I claim that in this setup, the vector space V as a G module is reducible. Okay? So why does it have a chance to be reducible? First of all, of course, it's a two-dimensional vector space, so we can find a one-dimensional vector space in it. Great. I mean, there's plenty of one-dimensional vector spaces. However, now we have to pick a very particular one-dimensional vector space. We have to take a one-dimensional vector space that is itself closed under the action of G. So let's look carefully, and again, this would be a perfect opportunity to have somebody of you say something, but it's rather hard in this setup, so let me just give the answer. So if you look at the subspace that is given by the sum of E1 and E2, and I let this group act on it, so it just permutes E1 and E2, so every element in W stays in W, obviously, so this is also S2 stable. So we found a one-dimensional subspace of V that is stable by our group S2, meaning V is reducible. So so again, I mean, you will get some of the exercises, and one of the exercises is actually that I want you to show that if you have an abelian group, so in particular, this would be an example of an abelian group, every module of dimension greater than 1 is reducible. Okay? Let me just give you a little hint how to do this, and the hint essentially is almost already the solution, but just think of what you know about, take it in the terms of matrix algebras, and think about what you know about matrix algebras that commute. And there's something that you've learned in linear algebra, I hope, about families of commuting variables. and their eigenspaces, and that will definitely help in this exercise. Okay, so in some sense, the idea of these irreducible representations is that they sort of are the building blocks of our G modules. So what I want them to actually do is I want to take a reducible G module like the one that I had previously, and I want to decompose it into irreducibles in the same way that I can look at a vector space of positive dimension and I can write it as the sum of vector spaces of dimension 1. And that this is in fact possible is a theorem. It's not obvious. It's a theorem. It's due to Maschke, and it says that if I have a finite group and a field of characteristic 0, I pointed this out here because it will be important in the proof, then every positive finite dimensional vector space V, which is also a G module, is in fact the direct sum of irreducible G modules. So that means I can write my G module as the direct sum of W1 up to WL. So that's where I actually want the finiteness, that the sum is finite, such that all of these WI's are themselves irreducible. Okay? So up to now, we didn't have any proof, so it was all a lot of digestion. Let's try to prove the theorem very easily. Okay, and I want to argue by induction. So the first step is, if I have a one-dimensional vector space, a one-dimensional G module, we already know that it's in particular irreducible. Okay, that's easy. So let's take a V of dimension greater than 1. So if this is irreducible, of course, there's nothing to do, so we don't have to go into this scenario. So we can assume that it's reducible, so that there is a non-trivial G-stable submodule W in V. Okay, so in order to establish now the theorem, we need to find a complementary G module. So another G module such that W plus this complementary direct sum with this complementary G module gives actually my G module V. How do I do this? And the trick is we start with an inner product on V and we define a G invariant inner product. And the way we define this G invariant product is a kind of universal trick. So I want to spend at least half a minute on that. It's just with a very, very easy construction actually. So I define a new inner product just by averaging over the group action. So I take 1 over G and the sum over all group elements, and I have the group act on both arguments of my inner product. And then one has to show that this again gives an inner product, of course. That's not hard to see. But then obviously from its construction, it is a G invariant inner product. Meaning whenever I take V1 and V2, then also G of V1 and G of V2 will have the same inner product. Okay, why did we do this? Now, it gives us a way to define the non-trivial submodule that is complementary to W, just by considering its orthogonal complement. So I look at the orthogonal complement of the W. So this is by definition, with respect to our G invariant inner product, this is by definition nothing than just all the V in V, such that the inner product with all W in W is 0. So now I claim that this is also a G module. And this is very easy, of course. Why? Because this is essentially due to the invariance of the inner product. So whenever I take an element that is in here and I apply the group G to both sides of this thing, I get another element W here. But our space W is closed by the group action. So essentially, the elements that are 0, that are in the orthogonal complement, will be fixed by the group. So I also want you to think about this at home, but it's really easy. I essentially did it. And now this gives us exactly the claimed complementary space. We have V is the direct sum, is actually the orthogonal sum of V and V perp. And since both of them now have smaller dimension, we can argue by induction. Okay, let me just so there was two private questions. So one question was to state the theorem again. I state the theorem again. The theorem is just every reducible representation is the direct sum of irreducible representations, or it's completely reducible. And the other question was, and this is, I mean, not the complete answer to that question, but the other question was the question to say something about positive characteristic. And this is maybe a good point to talk about positive characteristic. So what could happen? So this theorem essentially needs characteristic 0 to be true. What could go wrong? I mean, it also, I mean, so it seems that it needs two things. It needs the group to be finite, and because that's the way we defined this inner product here. But I mean, this can be dealt with in more generality for so-called reductive groups. But it also needs the fact that my group order here is not a zero divisor in my field. Otherwise, this wouldn't make sense either. So this Maschke theorem is one of the crucial corner points where things can be a little bit more messy if you are in positive characteristics. Okay. Oh, is the question? There's a very good question from Bernard to everyone. Very good. This decomposition is not unique. It's very important to point this out, and I should have pointed this out. It's not by no ways unique. There is another decomposition which actually is unique. It's a more cursor representation. It's the so-called decomposition into isotypic components. This one is unique. This one here is not unique. Okay, so why should I actually care about irreducible G modules? So up till now, it all looked a little bit as a very interesting exercise in a mixture of linear algebra and algebra, but why should you and I care about when we want to do something about semi-definite programming? And now we come to a very crucial statement. I call it a theorem, but its name actually has the name lemma. It says that whenever I have two irreducible G modules, V and W, and I look at a G homomorphism, so a map, a linear map that respects the group action, then this can be either zero or it is in fact an isomorphism. So in particular, a G homomorphism from V to itself is equivalent to multiplication by a scalar. Okay, so this theorem, this Schur's lemma, actually tells us that the notion of a G homomorphism is a particular I'm just looking always with one eye to the chat. Yes, so very good example, Fabrizio. A trivial action on a bigger dimensional vector space of dimension greater than 1 is nothing more than a vector space, and every vector space then is again every sub-vector space then is again a trivial representation. So this theorem tells us that the notion of a G homomorphism is in fact very restrictive. So there are not many G homomorphisms between irreducible representations. Why is this the case? It's a very easy proof, so let's try this also. So if I start with a G homomorphism, then one also sees very easily that both its kernel as well as its image are again G invariant sets. Yeah? That's just because the homomorphism is a G homomorphism. So, but then if my phi would neither be an isomorphism nor the zero map, its kernel would be a non-trivial submodule of V, and its image would be a non-trivial submodule of W. And then we can build up a contradiction. Yes, so I see that some of the questions that I'm not was not making aware of actually are answered themselves. Very good. So let's make this notion a little bit more lively. So let's look at some important corollaries. So again, an important corollary is that whenever I have an irreducible representation V, then its endomorphism ring is just K itself. That was already in the statement. So whenever I have another irreducible representation, W, and V, any other representation, then I can ask myself, how often do I find a representation that is isomorphic to W in V? This is what I call the multiplicity of irreducible representations isomorphic to V that are contained in V. So how many? So I look at my V, I know my V can be decomposed into irreducibles. This decomposition does not need to be unique, as we saw. However, when I write one down, how often do I get a representation that is isomorphic to my given W? And then we see that this is exactly the dimension of the space of G homomorphisms from W to V. And another important corollary is then whenever I take two characters that correspond to distinct irreducible representations, then they are orthogonal to each other with respect to the inner product that we defined previously. Okay, let's spice this up a little bit more. So let's make it a little bit more concrete. So I take a vector space V that is a G module, and I decompose it into irreducibles. And now these Mi, M1, M2, and up to Mk, they are numbers that sort of correspond to these multiplicities that I talked to. So it means that I have in my V M1 times the representation W1, M2 times the representation W2, and Mk times the representation Wk. That's a little bit maybe a flopsy way of noting it, but it's very convenient. And we will further assume that each of these irreducible representations Wi has a dimension Di. Then I claim that there's a basis of V that has the property, the first property is that the matrices that I get when I look at the matrix representation of G, M of G with respect to this basis, then these are of a very, very neat form. Essentially, they are themselves direct sums of smaller matrix representations, namely the matrix representations corresponding to W. That is essentially obvious from the way that this was written down. So because we know that a module, irreducible model is in particular a module itself, and that means that the group action leaves it invariant, so it's closed under the group action. So if I get the spaces that respects this decomposition here, the matrices that I get from my group operations, they should also make sure that I never leave any of those irreducible submodules. So that's why I get this representation here. And furthermore, the basis change actually affords an isomorphism, which shows that my endomorphism ring is the direct sum of smaller dimensional algebras, which are of dimension Mi times Mi. Okay, and we call the basis in the corollary above a symmetry adapted basis. So essentially, I want you to work out these details of this corollary in the homeworks, in the exercises, but essentially this is all just Schur's lemma applied in all the different possibilities. So you start with the case that all of them are 0 except 1 is 1. Then you look at the case what happens when 2 of them are 1, 3 of them are 1, and so on. And then you build them up to the statement that is here. And then it's essentially Schur's lemma over and over again. Okay, but this looked all a little bit less intriguing maybe. Let's make it a little bit clearer, even more. So again, I start with rho, now matrix representation, and I take a matrix X that has the property that it commutes nicely with the group action. So it doesn't matter from which side I multiply my group representations at for all elements of the group. So now if I further assume that my representation decomposes in the following way as previously again, then we can actually find a symmetry adapted basis of Kn in order to block diagonalize the matrix X. So there exists a matrix T with the property that when I do the base change, I mean that matrix of full rank T, that is a new basis, and whenever I do the base change according to T, I get a matrix Y that has block diagonal structure. What can I say about this block diagonal structure? Well, it will consist out of K blocks Yi. Each of them is of dimension midi, and they correspond to the different irreducible representations that are in here. And furthermore, one can show that these blocks further decompose into di equal blocks bi, which are of dimension mi. That sounds completely horrible maybe and undecipherable. Let me just write it down in a neater way. So essentially, you get a base change such that you get a the big matrix Y in the form. It consists of these smaller matrices yi to yk, and each of those matrices further is block diagonal with equal blocks bi. So what is the interesting thing now? And this has something maybe to do, at least in my mind, with the picture that I showed in the beginning. Somehow this is the very easiest way of representing our matrix X by taking into account its invariance that is defined in this equation here. Namely, when I want to know, for example, things about this matrix that relate to its eigenvalues, for example, I just look at the matrix Y, it has the same eigenvalues. If I want to look at if this matrix is, for example, positive semi-definite, I only need to look at one of those blocks here, these BIs. If one of them is positive semi-definite, all of them will be positive semi-definite. So this was also a little bit quick now, maybe. And again, I want in the exercises, I will guide you to actually making this more concrete. Oh, how does this relate to Artin-Wedderburn? Very good question. In some sense, this could be also called Artin-Wedderburn theorem. Very good remark. So essentially this, I mean, this here is essentially Artin-Wedderburn theorem. You know, in a much more, I mean, Artin-Wedderburn talks about, forgets about the group structure in some sense. Why does it preserve PSD? Well, very good question. Let me come to this in a minute, and it will make maybe more sense. It does. I mean, so for the moment, it doesn't necessarily. We only did a base change, so it preserves PSD-ness, of course. But we want something more essentially, and this is. When we come to the STPs, we don't only want the positive semi-definiteness to be preserved, but we want actually the eigenvalues to be preserved. So then we will need to essentially use orthogonal matrices instead of just inverting matrices here. So let me just, so after this very great, I mean, very dense and very short introduction or glance in representation theory, let me just give you for the moment pause here and give you a take-home message. Take-home message. So what's the take-home message? So suppose you don't remember anything from the details, which is completely fine, and I won't blame you for that. But what you should take home from the first part of this from this lecture is that whenever you have a linear, and this is a very, very simple message, whenever you have a linear group action on a vector space, then you can find very nice bases, actually, not only very nice bases, but actually several very nice bases. Some of them might be even orthogonal, which make linear maps, matrices, that are compatible with the group action potentially much simpler. And understanding the group action helps you to see how much you can actually gain out of this exercise. And because this was all very dense and very content rich, I would also like to hint you to a very nice book. I think this is the best book that I have read on this topic. But again, this might be just my personal preference for the author. Is this book by Serre, Linear Representations of Finite Groups. And if you are scared of the name Serre, then in particular, I invite you to read this book, because it's actually a book that is very nicely written and very instructive in many ways. So it will, as a lecture for maybe for tomorrow and the day after tomorrow, actually help you very much understanding what I've been saying. But my lecture was called Symmetries in SDPs. And this was a little bit related to the question that Monique hinted to. What does this have to do with SDPs? So you all know what an SDP is, so I don't need to go through the definition in all details, but let me just say that for convenience, I will use a notion that is a little bit more general, namely I will use SDPs with Hermitian matrices. Okay? That's just because then we don't, then we actually can assume that we have our algebraically closed field K again. And then a semi-definite program for me is, again, nothing more. It's given by Hermitian matrices C, A1 to AM, and a linear vector B. And then this naturally defines the semi-definite program that is laid out here. So you all should maybe have seen a semi-definite program, at least if you were a part of the POEMA lectures in Florence. But just keep in mind that for now we're actually working with Hermitian matrices. But it doesn't really matter too much, because essentially that's equivalent, because whenever you have a complex matrix, you can turn it a complex Hermitian matrix, you can turn it into a symmetric positive semi-definite matrix if necessary over the double dimension. Okay, so let's see how what we did before actually comes into play now. So again, I look at my space Kn, and then I have a finite group action on it, and I choose an orthonormal basis for Kn with respect to my G invariant inner product. Okay, always do that. At least if I'm in the setup where we have that, and then that means that the matrices that I get are unitary matrices. And then I can actually have them operate on the Hermitian matrices. They don't destroy the hermitivity of the matrices. And I can just define a group action by saying, well, I multiply from the left and from the right, one time with G, and then with this Hermitian conjugate. Okay. So this gives me an action on the Hermitian matrices, and then the Hermitian matrices get in that way the structure of a G module. Now I call a set, any subset of Hermitian matrices, I call invariant with respect to the group, if whenever I have a matrix in L, also it's the matrix that I get by having any group element act on the matrix is again in L. So in particular, of course, because the Hermitian matrices are a G module, they are themselves invariant with respect to G. But of course, I can look at other invariant sets. And then I also look at a linear functional, and I say that this linear functional is invariant if, it doesn't change its value whenever I plug in, instead of my original X, the group acting on my matrix X. And then I say that SDP is G invariant if both the cost function as well as its feasible set are G invariant. Okay, is this definition clear? It's not so surprising, I guess. So let's look at the following. So whenever I have an STP, I can actually look at a different STP, which I call, and its optimal value I will denote by y sub g, and that's essentially my original STP, but now I add an additional constraint. I only want matrices that are invariant with respect to my group G. Okay, so I add additional constraints. And obviously, because I add conditional constraints, my problem gets only harder. So I have this obvious inclusion that I basically wrote in the wrong direction, in the right direction. Very good. Okay, but now the interesting thing is, if my original STP was G invariant, then I actually have that the value that I get here will actually agree with my original value. So I have that the symmetrized version gives the same optimal value, not necessarily the same solution. So why is this the case? Well, this is very easy to show. Suppose I have a feasible solution and I take a group element G, then of course also the matrix XG is feasible because we assumed our STP to be G invariant. And in particular, we also have that there, because it's G invariant STP, that's why we set it up, actually also their cost function gives the same value. Okay. But now comes a fundamental, not a fundamental, but an important observation, namely that we know that the feasible region is a convex set. So I can look at the following matrix that I denote X sub G, which is just the average again over all XGs. So this is the same construction that we used for the definition of the G invariant inner product. And this then again gives me a feasible solution, which again has the same objective value. And by definition now is G invariant. So it is a solution of my program up here. And thus we have the equation of the two optimal values. Okay, so in the first step, we can reduce, or we can take our initial STP and just freely add, if it's G invariant, we can freely add these many constraints to it and make it more constrained. Okay, so we can restrict to invariant matrices, so the commutator of my group action. And the interesting thing now is, and this was all the exercise about representation theory in Schur's lemma was about, is that we can find a basis now of my vector space that block diagonalizes the matrices. Okay, so I can even take this basis to be orthogonal, and now this will be a little bit a hustle of indices. I hope I got all the indices right. So I assume that my space decomposes in this form orthogonally. I have H11, H12 to H1mi. So these are my first irreducible representations. They are all pairwisely isomorph, and the decomposition here is not unique. Then I take the second set of irreducible representations, H21 to H2m2, and so on, until I come to the last set of irreducible representations, and I look at this decomposition here. I can use this to be orthogonal, and I can pick an orthonormal basis of each HL1 of the first one of those, of this one, and so on. And now, because we have that these are pairwisely isomorphic, I can find an isomorphism that makes these a map that makes this isomorphism concrete. So I have a map phi Li that maps HL1 to HLi. And in that way, I obtain an orthonormal basis for each of these HIs by just taking the orthogonal basis that I have here and mapping it to the others. And why do we do that? So this is now again a little bit brief. We actually do this because this will give us our block diagonalization. It will be a block diagonalization with orthonormal basis, so we don't have to worry about the PSD-ness anymore. This was Monique's question. And we can actually do this in a very nice way with so-called zonal matrices that are just defined by products of these inner products of these bases that I get in this way. So this is just a very technical definition. However, so the importance of the zonal matrices comes from the fact that an invariant matrix that is Hermitian and invariant is that defined via the zonal matrices in the following form. Its entry xij is the sum over the zonal matrices inner product with some matrices ML, and these MLs are Hermitian matrices of dimension Mi, and this R here should be a K. I'm sorry for that. Okay, so this is essentially a way of making this block diagonalization very concrete. So summing up what we actually proved in this way, or at least what I sort of wanted you to see, is that whenever I have a G invariant SDP, I can find an equivalent SDP and reduce, that is nicer in the sense that it maybe contains smaller matrices, and reduces my original SDP to that without losing the optimal value. So I have a new SDP, I have new variables that are smaller dimensional. Okay, so this looks all very nice and very technical, and this is essentially where all the meat still lies. I mean, the theorem is a very abstract one in the sense that I only talked about there exists, and this is was all very unconcrete. However, if you have a situation that you want to simplify, all these zonal matrices, the basis needs to be really carefully calculated. So this can be far from trivial. I mean, but it's essentially can be very important for you in the sense that it can make the difference, that can enable you to actually compute a given semi-definite, the value of a given semi-definite program that normally without this reduction methods you wouldn't be able to compute. Okay, so let me just we have still a little bit of time. I'm surprised how much time has already passed, but let me just give you one easy example where you see this in action. And the idea is that I want to do this with the theta number of a graph. So in order, I'm not sure if you all know what the theta number is. I want to just briefly motivate the theta number. So suppose I have given a graph with edges V, with vertices V and edges E. Then a subset of the vertices is called independent if no two elements in S are connected by an edge. Okay, and alpha of G is a graph parameter, and this is should denote the cardinality of the largest independent set in G. Okay, and additionally, we can also wonder about k-vertex coloring. So k-vertex coloring of G is the distribution of k-colors onto the vertices, such that neighboring vertices obtain different colors, and the chromatic number of G is the smallest k, such that there is a k-coloring of the vertices. Okay, these are very, very important graph parameters. They are very easy to do on small examples. So for example, here it's very easy to see that the independence number is 2. Why is that easy to see? Well, I mean, you pick 2 of them, and then basically you cannot do anything more. Then you can basically establish this by looking at all the possibilities, but of course this will be too much to do. Or let's also look at the chromatic number of this graph. So we have 2 colors here. I can color those 2 here, and then I need the 3rd color here. So I need 3 colors at least to actually color this graph. Okay. So why did I do this? Well, it turns out that this is a very hard parameter to compute for graphs in general, but there's a nice relaxation that you maybe have already seen. It's the theta number defined by Lovász. And for that, let me just motivate it a little bit. So I start with an independent set S, and I look at its characteristic function. So it's a function that takes either 1 or 0. It depends to each vertex, dependent if the vertex is in S or not. And with that function, I can just define an easy Hermitian matrix, actually a symmetric matrix, as defined here. So this is 1 over the cardinality of S if I and J are in S or 0 else. And this matrix satisfies two properties that are important. So whenever I sum over all elements, this gives me exactly the cardinality of S, and it is positive semi-definite. Okay. So why is this important? Well, actually, we can then look at the following semi-definite program, which is called the theta number of G, and the theta number looks at the supremum of the sums over the elements in the matrix X, such that X, I, J are 0 for every I, J that are edges, and such that the diagonal elements sum to 1, and that it is a positive semi-definite. So in particular, if I have an independent set, its associated characteristic function will give me such a solution. So this essentially gives a good gives an estimate for the independence number of my graph, and this is essentially the celebrated lower Sandwich theorem that says, well, the theta number upper bounds the independence number, and it actually lower bounds the chromatic number of the complementary graph, which is not so important now. So why is this nice? I mean, this gives us an SDP that we can calculate, but how do we actually calculate it? Let me just show you one easy example. So suppose we have a graph that is very, very simple, namely it's this cyclic graph, okay? So if you have this cyclic graph, then the theta number of the cyclic graph is obviously, by the definition, invariant by the cyclic shifting of the vertices in that way. That's why I drew it like this. So it gives us a semi-definite program that is invariant by the cyclic group. And when we actually want to do the math, we can actually look at a symmetry adapted basis of this representation in K to the 4, where this semi-definite program lives. And this is the classical Fourier basis. So it's the basis when I look at which is given in the set T here. And if you are afraid of complex matrices and Hermitian matrices, and you want your semi-definite program for all sakes to be real, you can of course also look at the matrix that you get by pairing complex conjugate ones here, and then you get the symmetry adapted real basis. But that's just a side remark. And so the important thing now is that when you do all the estimations here, you actually see that the semi-definite program that we get will be from a matrix that has 4 blocks. Each of them corresponds to, essentially the 4 entries here. But moreover, that these blocks are all one-dimensional, because each of the irreducible representations that actually occur in K1 are distinct. So essentially, we reduced our semi-definite program to a linear program, which is much easier to solve. And generalizing this, essentially, this idea, by taking the Fourier basis, one can actually get that every theta number of a k-gon is essentially a linear program, namely the linear program that is given here. And with the linear program that you get here, you can actually compute the theta number of the k-gon for all values of k rather easily. And this is what I would like you to do as a homework too. Okay, so this was a very, very, very rough and maybe fast invitation to semi-definite programming and symmetries in it. But there is luckily a lot of good literature that you can actually find rescue if, when whatever I was telling you didn't successfully invite you to learn more. So there is, here I only noted some of them. In particular, there is this very nice paper by Gattermann and Parillo from 2004. There is a very instructive handbook article by Christine Bachoc, Dion, Alex Schreiber, and Frank Valentin. in the handbook of semi-definite and conic optimization. There is an article by Frank about symmetry in semi-definite programs, which you can actually read to actually get the details that I was missing out. There's also a very nice article by Etienne about exploiting special structure in semi-diff programming. And if you're more interested in the numerical analysis, there is also this paper by Muro, Kano, and Takuchimas that talks about matrix star algebras, but hiddenly that's essentially maybe that's not the same story, but it's a complementary story in the sense that sometimes your matrices might have a group structure that you actually don't see, but what can you do in these instances? Okay, I hope that this was kind of understandable, and I'm looking forward to more questions, the ones that I maybe didn't answer. Oh, could you please remind why you insisted to deal with? So the only reason why I did this was that, so it's not the only reason, but it's essentially that it's, from the notation, it's a little bit more convenient, because in Schur's lemma, some of the consequences of Schur's lemma, you want the field to be algebraically closed. And so I just prefer to work over the complex numbers. But you don't necessarily need to do this. So what I was hinting to here is essentially that in most cases, you can just use the basis that you had over the complex number, over the complexification, to actually get a real matrix. So you don't necessarily need to do that, but it's just more convenient in some sense. Oh, okay, very good question. Corby, yeah, I like the name Corby because, just because it reminds me of my childhood name too. So what happens when you have an infinite group? So, there's different kinds of bad things that can happen, of course. If you have groups that are so big as the reals, for example, then you have problems. However, if you have so-called reductive groups, so these are all compact groups, which are, then you can, essentially what was important for us was this kind of averaging argument. And for reductive groups, you can still make sense of this. This is called the Reynolds operator. For compact groups, you can actually find, instead of using the average, you use the Haar measure on the group, and then you can essentially make sense of this averaging over the group that we did, and then the things work go through in the same way. Can you say something about generalization of G invariance of an SDP to the case where the data matrices belong to a matrix star algebra? Can I say something about that? Let me think about. So essentially what's the difference is, essentially what you want, and this was, at some point Monique asked us too. So essentially you want to find this isomorphism that makes this block diagonalization happening. And if you have a group behind, just knowing about the group makes this isomorphism better understandable. But in some sense, it's the same story, just in a different disguise, I would say. Does this make sense? I'm not sure if this answers your question, Etienne, but feel free to say something yourself as the chair of the committee yeah. So there are, of course, there are not all of them are group commutants. Yes. So it's the same story in the sense that you have again this isomorphism. But you cannot get it from the group in that sense. So it's much more difficult, I would think.
So Cordian, it looks to me like you've answered all the questions. Do you also?
Oh no, there's another one.
Okay.
Oh, did you ever see a quaternionic group? No, I never saw a quaternionic group. So a quaternionic group is a group where now I have to get the definition correctly, is a group. So this is related a little bit to the question that Monique asked, and that I sort of hope to answer without somebody pointing out. So it's a group where you cannot just naively do what I did, so that naively do in the sense that not always you will have the possibility of getting a real basis in this easy way that you just pair complex conjugates to each other. So I've never seen such a thing in practice, but yeah, so what do I know about the practice anyways? But you can also deal with those groups, of course. It's just much more careful. Okay. So of course, if this was a little bit too quick and in practice, the symmetry adapted basis can look quite complicated. I agree. Are there tricks how to calculate the zonal matrices from these more efficiently? I would like to know, depending on what you mean by more efficiently, but I would like to know the trick. So there are, this is why I pointed out this, there are, what Etienne also said, if you have a matrix algebra, you actually want to look at its commutant. And there are algorithms to actually do that too. But Etienne is a little bit maybe more the, the expert on that. There's a brand new paper. Wow, this is interesting. I don't know this paper now, and I only see its archive number, so it's a little bit hard to say. But yeah, so I think you can do things numerically very, very good. But this is just very nice because it's sort of I like this approach from the sense because you don't really have to deal with. If you have the huge matrix algebra, you need to work with the huge matrix algebra. It might be already so big that you cannot do anything with it. And in that sense, basically the group, understanding the group action helps you to sort of immediately modulo the problem that you have to get these bases, of course, but avoids this huge matrix algebra that you don't have to deal with. If you can deal with huge matrix algebras, then you don't maybe need the group representation so much.
Yeah, I think a good example is the automorphism group of the Hamming graph, which plays a role in binary code sizes. So you cannot do any algebra typically in these matrix sizes because they just grow like 2 to the n.
Exactly. Yeah, that's a very good example. So I think if you, now maybe naive. So if you have a matrix algebra and you can deal with it, calculating its commutant, there are good algorithms to do that. I think there's a random algorithm that mostly works correctly, right? But it's sorry, I have to read again. Following the question, which have G invariants of SDP? How to detect if I have a decomposition? Oh, that's a good question.
Maybe I can just answer that, Cordian. There is an algorithm to find the smallest matrix star algebra, at least coherent matrix star algebra that contains given matrices. So you can take the SDP data matrices and run this algorithm to find the smallest coherent algebra that contains them. So it's called the Weisfeiler-Lehmann algorithm. And the coherent algebra means it has a 0-1 basis.
Mm-hmm. So, but for how big matrix algebras does this actually work in practice?
Well, the algorithm is polynomial time, but again, you have to be able to do linear algebra in this site.
Okay. I have applied it on problem size 20,000 to 20,000. Okay. It's good, but yeah, 2 to the n grows quicker than that.
Okay, so Cordian, I think since we will have more opportunities to hear you lecture on these topics, same time in the next 2 weeks, perhaps we can leave a discussion here.
Yes,
And so I would just like to thank you on behalf of all the participants for this very nice presentation. And we really look forward to seeing you same time next week, same place.
Okay, yes. Thank you, everybody. And yeah, see you next week. And if you have questions, feel free to also contact me by email.
Okay, and also thank you very much to all the participants. And I hope all of you will join us again next week. Thank you.
Bye-bye.
Bye.